In theoretical computer science and formal language theory, a regular expression is a sequence of characters that define a search pattern, mainly for use in pattern matching with strings, or string matching, i.e., find and replace, like operations. The concept arose in the 1950s, when the American mathematician Stephen Kleene formalized the description of a regular language, and came into common use with the Unix text processing utilities ed, an editor, and grep, a filter. In modern usage, irregular expressions are often distinguished from the derived, but fundamentally distinct, concepts of regex or regex, which no longer describe a regular language. See below for details. Regex are so useful in computing that the various systems to specify regex have evolved to provide both a basic and extended standard for the grammar and syntax. Modern regex heavily augment the standard. Regex processes are found in several search engines, search and replace dialogues of several word processors and text editors, and in the command lines of text processing utilities, such as sed and awk. Many programming languages provide regex capabilities, some built-in, for example, Perl, JavaScript, Ruby, awk, and TCL, and others via a standard library, for example, net languages, Java, Python, POSIX, and C++. Most other languages offer regex via a library. Patterns. The phrase regular expressions is often used to mean the specific, standard textual syntax for representing patterns that matching texts need to conform to. Each character in a regular expression is understood to be a metacharacter, or a regular character. Together, they can be used to identify textual material of a given pattern, or process a number of instances of it. Pattern matches can vary from a precise equality to a very general similarity. The metacharacter syntax is designed specifically to represent prescribed targets in a concise and flexible way to direct the automation of text processing of a variety of input data in a form easy to type using standard ASCII keyboard. A very simple case of a regular expression in this syntax would be to locate the same word spelled two different ways in a text editor. The regular expression serialize SZE matches both serialize and serialize. Wildcards could also achieve this, but are more limited in what they can pattern. The usual context of wildcard characters is englobing similar names in a list of files, whereas regex are usually employed in applications that pattern match text strings in general. For example, the regex $T plus $$ matches excess white space at the beginning or end of a line. An advanced regex used to match any numeral is $D plus $. See examples for more examples. A regex processor translates a regular expression in the above syntax into an internal representation which can be executed and matched against a string representing the text being searched in. One possible approach is the Thompson's construction algorithm to construct a non-deterministic finite automaton, which is then made deterministic, and the resulting DFA is run on the target text string to recognize substrings that match the regular expression. The picture shows the NFA scheme N obtained from the regular expression S**, where S denotes a simpler regular expression in turn, which has already been recursively translated to the NFA-N. History. Regular expressions originated in 1956, when mathematician Stephen Kleene described regular languages using his mathematical notation called regular sets. These arose in theoretical computer science, in the subfields of automata theory and the description and classification of formal languages. Other early implementations of pattern matching include the SNOBOL language, which did not use regular expressions, but instead its own pattern matching constructs. Regular expressions entered popular use from 1968 in two uses. pattern matching in a text editor and lexical analysis in a compiler. Among the first appearances of regular expressions in program form was when Ken Thompson built cleaned notation into the editor QED as a means to match patterns in text files. For speed, Thompson implemented regular expression matching by just-in-time compilation to IBM 7094 code on the compatible time-sharing system, an important early example of JIT compilation. He later added this capability to the Unix editor ed, which eventually led to the popular search tool grep's use of regular expressions. Around the same time when Thompson developed QED, a group of researchers including Douglas T. Ross implemented a tool based on regular expressions that is used for lexical analysis in compiler design. Many variations of these original forms of regular expressions were used in Unix programs at Bell Labs in the 1970s, including Vi, Lex, Sed, Awk, and EXPR, and in other programs such as Emacs. Regex were subsequently adopted by a wide range of programs, with these early forms standardized in the POSIX-2 standard in 1992. In the 1980s, the more complicated Regex arose in Perl, which originally derived from a Regex library written by Henry Spencer, who later wrote an implementation of advanced regular expressions for TCL. The TCL library is a hybrid NFA/DFA implementation with improved performance characteristics, earning praise from Jeffrey Friedel, who said, "It really seems quite wonderful." Software projects that have adopted Spencer's TCL regular expression implementation include PostgreSQL. Perl later expanded on Spencer's original library to add many new features, but has not yet caught up with Spencer's advanced regular expressions implementation in terms of performance or Unicode handling. Part of the effort in the design of Perl 6 is to improve Perl's Regex integration, and to increase their scope and capabilities to allow the definition of parsing expression grammars. The result is a mini-language called Perl 6 rules, which are used to define Perl 6 grammar as well as provide a tool to programmers in the language. These rules maintain existing features of Perl 5x Regex, but also allow BNF-style definition of a recursive descent parser via subrules. The use of Regex in structured information standards for document and database modeling started in the 1960s and expanded in the 1980s when industry standards like ISO/SGML consolidated. The kernel of the structure specification language standards consists of Regex. Its use is evident in the DTD element group syntax. Starting in 1997, Philip Hazel developed PCRE, which attempts to closely mimic Perl's Regex functionality and is used by many modern tools including PHP and Apache HTTP Server. Today Regex are widely supported in programming languages, text processing programs, advanced text editors, and some other programs. Regex support is part of the standard library of many programming languages, including Java and Python, and is built into the syntax of others, including Perl and ECMAScript. Implementations of Regex functionality is often called a Regex engine, and a number of libraries are available for reuse. Basic concepts. A regular expression, often called a pattern, is an expression used to specify a set of strings required for a particular purpose. A simple way to specify a finite set of strings is to list its elements or members. However, there are often more concise ways to specify the desired set of strings. For example, the set containing the three strings, handle, and harundle, can be specified by the pattern handle. We say that this pattern matches each of the three strings. In most formalisms, if there exists at least one regular expression that matches a particular set, then there exists an infinite number of other regular expressions that also match it. The specification is not unique. Most formalisms provide the following operations to construct regular expressions. Boolean, or a vertical bar separates alternatives. For example, gray can match gray or gray. Grouping parentheses are used to define the scope and precedence of the operators. For example, gray and gry are equivalent patterns which both describe the set of gray or gray. Quantification: a quantifier after a token or group specifies how often that preceding element is allowed to occur. The most common quantifiers are the question mark, the asterisk, and the plus sign plus. These constructions can be combined to form arbitrarily complex expressions. Much like one can construct arithmetical expressions from numbers and the operations plus, minus, times, and divided by. For example, h_del and h_del are both valid patterns which match the same strings as the earlier example, h_del. The precise syntax for regular OR expressions varies among tools and with context. More detail is given in the syntax section. Formal language theory. Regular expressions describe regular languages in formal language theory. They have the same expressive power as regular grammars. Formal definition: regular expressions consist of constants and operator symbols that denote sets of strings and operations over these sets, respectively. The following definition is standard, and found as such in most textbooks on formal language theory. Given a finite alphabet sigma, the following constants are defined as regular expressions, denoting the set. Epsilon denoting the set containing only the empty string, which has no characters at all, and sigma denoting the set containing only the character A. Given regular OR expressions R and S, the following operations over them are defined to produce regular expressions. RS denotes the set of strings that can be obtained by concatenating a string in R and a string in S. For example, ab c d f equals abt a b e f c d c e f. RS denotes the set union of sets described by R and S. For example, if R describes ab c and S describes ab d f, expression R S describes ab c d f. R asterisk denotes the smallest superset of set described by R that contains epsilon and is closed under string concatenation. This is the set of all strings that can be made by concatenating any finite number of strings from set described by R. For example, 0, 1, asterisk is the set of all finite binary strings, and ab c asterisk equals epsilon ab c abab abc cab cc abab abcab. To avoid parentheses, it is assumed that the clean star has the highest priority, then concatenation, and then alternation. If there is no ambiguity, then parentheses may be omitted. For example, C can be written as ABC, and A can be written as of BC asterisk. Many textbooks use the symbols plus or for alternation instead of the vertical bar. Examples: A, B asterisk denotes epsilon, A, B, 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 B. Asterisk denotes the set of all strings with no symbols other than A and B, including the empty string. Epsilon, A, B, A, ab, bar, B, B, R. Ab asterisk denotes the set of strings starting with A, then 0 or more, B, S, and finally optionally A, C. Ab, A, B, C, ab, A, B, B, C. Asterisk 1 asterisk denotes the set of binary numbers that are multiples of 3. Epsilon 0, 00, 11, 000, 011, 110, 0000, 0011, 0110, 1001, 1100, 1111, 00000. Expressive power and compactness. The formal definition of regular expressions is purposely parsimonious and avoids defining the redundant quantifiers, and plus, which can be expressed as follows. A plus equals a asterisk, and a equals. Sometimes the complement operator is added, to give a generalized regular OR expression. Here RC matches all strings over sigma asterisk that do not match R. In principle, the complement operator is redundant, as it can always be circumscribed by using the other operators. However, the process for computing such a representation is complex, and the result may require expressions of a size that is double exponentially larger. Regular expressions in this sense can express the regular languages, exactly the class of languages accepted by deterministic finite automata. There is, however, a significant difference in compactness. Some classes of regular languages can only be described by deterministic finite automata whose size grows exponentially in the size of the shortest equivalent regular expressions. The standard example here is the languages LK consisting of all strings over the alphabet A, B, whose kth from last letter equals A. On one hand, a regular expression describing L4 is given by generalizing this pattern to LK gives the expression. On the other hand, it is known that every deterministic finite automaton accepting the language LK must have at least two K states. Luckily, there is a simple mapping from regular expressions to the more general non-deterministic finite automata that does not lead to such a blow-up in size. For this reason, NFAs are often used as alternative representations of regular languages. NFAs are a simple variation of the type 3 grammars of the Chomsky hierarchy. Finally, it is worth noting that many real-world, irregular expression engines implement features that cannot be described by the regular expressions in the sense of formal language theory. Rather, they implement regex. See below for more on this. Deciding equivalence of regular expressions as seen in many of the examples above. There is more than one way to construct a regular expression to achieve the same results. It is possible to write an algorithm that, for two given regular expressions, decides whether the described languages are equal. The algorithm reduces each expression to a minimal deterministic finite state machine, and determines whether they are isomorphic. The redundancy can be eliminated by using clean star and set union to find an interesting subset of regular expressions that is still fully expressive, but perhaps their use can be restricted. This is a surprisingly difficult problem. As simple as the regular expressions are, there is no method to systematically rewrite them to some normal form. The lack of axiom in the past led to the star height problem. In 1991, Dexter Kozin axiomatized regular expressions with clean algebra. See clean algebra #history for details.